So back in step 2, what we did was we wanted to be on the surface of the planet. So we said x massive plus the planet radius. So that put us on the surface of the planet. But now we're not working with planets anymore, we're working with a black hole. So we're going to change it to a numerical value just to see how far away we are from the black hole. So I'm going to replace what it says here, planet radius, to 50. And because 50 was a planet radius, but just to have a numerical value, I'm going to change that. So down here where I have, it says x massive plus planet radius. I'm going to delete this and type in 50. So let's see what happens when I do this. So it seems like our particle or little blob or whatever is just orbiting around the black hole. So I want to find a radius where it can potentially escape this black hole. So let's try, instead of 50, let's give it a radius of 70. So let's see what happens then. Seems like it's escaping, but ultimately looks like it's coming right back. Okay, so 70, it's still bound. Let's try 90 and see what happens. That looks a bit more promising. So you can see it's just still going out, and the velocity is still increasing. So it seems like we found a radius where our particle traveling the speed of light has escaped the black hole. So we saw at 70 it was still bound, 90 now it's escaping that black hole. So let's try to go in the middle and see if we could get a better radius, and let's pick 80. What happens there? Seems like 80 is working.
Yes. I think it might just barely escape on 80.
Seems like it.
Yeah.
So
no signs of coming back now.
Mm-hmm. So this means that just like with the planet, that the radius, we found the radius, well, the planet, we're on the surface of the planet, and at that distance from the center, we were able to escape. At this radius from the black hole, we are also able to escape.
Okay. So for a mass of 3, we found that the dividing line between an object being able to escape and not being able to escape looked to be about 80 based on just playing around with numbers a little bit. Mm-hmm. But let's see if that actually changes with the mass. So for example, it might be intuitive to you or me that if I make the mass, instead of 3, I make it a smaller number, maybe at the same radius of 80, we could escape. So how about we try going from 3 to 1 or something?
Okay.
Okay. Here, Daniela just changes 3 to 1. We keep our radius the same, and
we're still escaping.
It looks like we're escaping. Okay.
What about if we try a smaller number?
Like 0.5 maybe?
Yeah, let's try that.
All right.
0.5.
That should... Oh. Okay, we're still
working.
escaping.
Mm-hmm.
How about we try to go for 0? Right? Because if I'm trying to model light, then light is actually massless.
So if we try 0.
Okay. Where is it?
Doesn't seem to be working.
Okay, so what's wrong with this? Why can't we have a mass of 0? Is there somewhere in the code, I think, we might have some kind of... We don't get any error message. Oh, I see the problem. See, somewhere about right down here, we have to divide by the mass in order to get this acceleration. So we're updating our delta Vx and our delta Vy by saying we're going to define, for example, delta Vx by the acceleration times our change in time. Our acceleration is given by the force with which we launch the object, because of gravity and stuff, and divide that by our mass. But if our mass is 0, the computer gets some non-zero number divided by 0, which causes a problem. In fact, we can't even draw an object here. So if we want to approximate the effects of a photon, then we just have to go for smaller numbers. So before we try 0.001, you can try 0.3 zeros and a 1, or 4 zeros and a 1, or any unimaginably small number you can think of. And it's not going to really change anything, but the code could actually run with those numbers.
I see. So setting it to a mass of 0 breaks the code.
Mm-hmm.
So let's try a number very, very close to 0. I see. Now it'll run.
We escape. And, that's as much of a proof as we can give right now. But we can better solve for this actual radius by going to the board.